here we take a capacitor with a cylindrical configuration. I need to calculate the capacitance C of this capacitor. As you see, we have a cylindrical shell, negatively charged, minus Q, and inside we have a rod with lambda charge density. It's a negligible thickness. I need to calculate the capacitance. You know, C equals to Q delta V, and delta V equals to minus E dot dr. Okay, so to calculate C, I need to calculate delta V. How can we calculate delta V? Before we have to find E between in this region. Okay, we have to find E. To calculate E, we can use Gauss's law. Here in this figure, we have a top view. We are looking from here. As you see, between the rod and the cylindrical shell, we have field out of the rod because the rod is positively charged. So I need to calculate this field. We can select a cylinder with radius r and length L as Gaussian surface, and with the conditions we have to write E must be parallel to dA, E must be constant, and also E must be radial. Phi equals to E dot dA equals to Qn divided by epsilon. Okay, as you see here we have Gauss's, this one, Gauss's surface. Okay, if you look well here, it must be between. It's a cylinder inside with a length L. Okay, we can take the length of Gauss's also equals to L. Okay, anyway, we can write, let me clean before. We have phi equals to E. You know, E is out and dA is out. Okay, here we have dA, and here also we have E. The angle between them equal to 0. We can write E dA cosine 0 equals to Qn. Inside the Gaussian surface, we have the positive charge Q. It's a rod. It's a rod with length L. So Q inside equals to lambda times L, because we have the total length of the rod inside Gaussian surface. is inside Gaussian surface. So Q equals to lambda L divided by epsilon. Okay, so E is constant. E is constant at any point on Gaussian surface. Be careful. I'm talking about at any point here. E is constant. But E is not constant between the two plates. E here is not equal to E here. But on the pointed line, E is constant. So we can put E outside. We get E dot A equals to lambda L divided by epsilon. A is the area of Gaussian surface. This one. You know, we have R as radius and L as length. A equals to the perimeter 2 pi R times L. Okay, so E equals to lambda L divided by 2 pi, 2 pi R L epsilon 0. We can eliminate L and L. We get finally lambda divided by 2 pi R epsilon 0. So we can write finally E in function in terms of Q. We can substitute the value of lambda, you know, uh, lambda or Q equals to lambda L. So lambda equals to Q divided by L. Okay, this is the value of E. We can substitute the value of E in this relation to find delta V. Okay, so finally we have delta V and we have E. Let me we can write lambda times divided by 2 pi epsilon 0 R times 2 divided by 2. Okay, just to put K in the place of 2 times 2 times pi times epsilon 0. We get 1 divided by 4 pi epsilon 0, which is equals to K. Okay, so here we get 2 lambda K divided by R. We substitute the value of E. We get delta V equals to minus, you see, here I want to calculate delta V between the distance A and B, okay, in this region. Okay, so it must be between A and B. You see here, A is small in terms of the length of the road, okay? For this reason, we used lambda, because it's a negligible value anyway. Here we can write E, the angle between E and dr. Dr is the distance between A and B, like this. So the angle between E and dr equals to 0. We can say here we have dr. Okay, and here we have E. So we can write E dot dr times cosine 0. Okay, E equals to 2k lambda divided by r dr between A and B. You know, uh, we have minus 2 is constant, k is constant, lambda is constant. The integral of dr divided by r equals to ln r, okay, between A and B. So we can write, okay, equals to ln B minus ln A equals to ln B divided by A. Okay, so we can write finally ln B divided by A. Here we can say finally delta V equals to, we can put, we can eliminate this minus and we change A and B. Okay, 2k. Anyway, let me, here we can say delta V, you know, delta V equals to VB minus VA equals to minus 2k lambda ln B divided by A. You know, delta V final equals to the absolute value of VB minus VA. Okay, so we can calculate now C. Here we can say delta V equals to the absolute value of VB minus VA. Look here, you know, this value, as you see, this value is, is, is a positive value. Why? Because B is greater than A. So ln B divided by A is positive. Okay, so this one is positive. This one is positive, lambda. K is positive, positive. Here we have negative. So delta V must be the absolute value of VB minus VA. So equals to plus 2k lambda ln B divided by A. Okay, this value must be positive because if you have, for example, ln A divided by B, and you know A is smaller than B, in this case, ln A over B must be positive. So we have to change to get a positive value of delta V. You have to change between A and B. Anyway, here we can say C equals to Q divided by delta V. Q divided by 2k lambda ln B divided by A. You know, we can write Q equals to lambda times L if you want. Okay, this is the result anyway, the final result. But you can change. You can put C in terms of lambda. You can put Q equals to lambda L, or you can write lambda equals to Q divided by L. Okay, as you like. Okay, if we put lambda equals to Q divided by L, we can say C equals to Q, or let me write Q equals to lambda L divided by 2K lambda ln B divided by A. We can eliminate, cancel lambda and lambda. So here we have equals to L divided by 2K ln B divided by A. You can say the capacitance per unit length equals to 1 divided by 2K lambda B over A. This is the capacitance per unit length. I can ask you a question to find the capacitance per unit length of a capacitor uh, if in the case of a cylindrical configurations.